Percent composition. In the late 18th, early 19th century, two fundamental laws were found by chemists. First is the law of conservation of mass. Mass is neither created nor destroyed, credited to Antoine Lavoisier after Mikhail Lomonosov discovered it earlier. The law of definite proportion. A given compound always contains exactly the same proportion of elements by mass. That was stated by Joseph Proust based on his work and work done by Joseph Priestley and Antoine Lavoisier. Dalton's atomic theory. In 1803, John Dalton created his atomic theory with these postulates. Each element is made up of tiny particles called atoms. The atoms of a given element are identical. The atoms of different elements, therefore, have different masses, sizes, and other physical properties. Chemical compounds are formed when atoms of different elements combine with each other. A given compound always has the same relative numbers and types of atoms combined in the same proportion. Chemical reactions involve a reorganization of the atoms, which are changes in the way they are bound together, and atoms themselves are not changed in a chemical reaction. We've been able to calculate the molar mass of a material if we know its formula already. However, what if we encounter an unidentified substance? Using the tools we already have, along with the fundamental chemical laws, we are able to determine the composition of a substance if we have certain pieces of information. One such piece of information is the percent composition, or the percentage of a compound's mass made up by its elements. A compound is always made up of the same atoms and type in the same proportion. So on the left, we have potassium chromate, where we have 40.3% of it is potassium. Then potassium dichromate on the right here, only 26.5% is made up of potassium. You can see, hopefully you can see, we have different formulas for each one of these compounds. The percent by mass of an element in a compound is the number of grams of the element divided by the mass in grams of the compound, multiplied by 100%. So the percent of the element, number of atoms, times their atomic weight, divided by the formula weight of the compound, and you multiply that by 100. Here's an example. The percent composition of carbon and hydrogen in ethane, which is C2H6. So the percent of carbon will be 2, we have 2 atoms here, times its atomic weight, 12 AMU, divided by the atomic weight of ethane, which is 30 AMU. Multiply by 100, and we get 80%. For hydrogen, we have 6 hydrogens, atomic weight, 1 AMU, divided by 30 AMU, times 100, and we get 20%. Now, since ethane is made up of only carbon and hydrogen, if the percent composition of carbon was 80%, the remaining percent must be hydrogen. So you would have 100% minus the percent of carbon will give you the percent of hydrogen. So 100 minus 80, 20%. So here's our percent of hydrogen, 20%, and carbon, 80%. Even though there are more atoms of hydrogen in ethane, there is much less percentage of mass in the compound than that of carbon. That's because one carbon atom, 12 AMU, is much more massive than one hydrogen atom, which is only 1 AMU. Therefore, carbon accounts for a much greater percentage of the mass of ethane than hydrogen does. Let's work a problem with aluminum. Aluminum is used in soda cans, aircraft, automobile engines. Demand is increasing. Aluminum is isolated from an ore called bauxite, which is roughly 12% aluminum by mass. So what that tells us that for every 100 grams of bauxite, 12% of that is aluminum. So that would be 12 grams of aluminum for every 100 grams of bauxite. So let's put an arrow here. That's the aluminum, and there's the bauxite. So the question is, how much bauxite ore in grams must be mined to get enough aluminum to make a car engine that has 100 kilograms of aluminum in it? Try working it on your own for a second, and we'll pause here, and then we'll hit click and show you the solution. Okay, click. This is essentially a unit cancellation problem. We know we want 100 kilograms of aluminum, so we'll start with that. We know we have to get to grams, So we have our little conversion here, grams to kilogram. That gets rid of the kilograms here, and we now have 10 to the 5th grams of aluminum. And here's the big thing right here. And that came from our numbers up here, where we said you need 100 grams of bauxite ore to get 12 grams of aluminum. Now we put it this way so we could have the grams of aluminum, which is in the denominator here, cancel out with the grams of aluminum in the numerator. And that's going to leave us with grams of ore. And when you do the math, you need 830,000 grams of ore to get 100 kilograms of aluminum. And sorry about mixing the grams and kilograms there, but it's good practice.